dear colleagues, thank you for this opportunity to present our results, mutual results of research study of Sevastopol State University and Institute of Natural and Technical Systems. And I try to do my presentation in English, to be more understandable for our foreign colleagues. My presentation entitled like Ontology-based and practice-oriented digital model of environmental monitoring. Very complicated title, but I'll try to explain why is it so. On this slide, it is a concept of digital twin of coastal region geosystem. You know that there is one of the main goals of our global development is sustainability, so sustainable development. And you know maybe that there is a list of goals of sustainable, of achieving of sustainability of our society, which is formulated by UN, United Nations. And one of the cutting-edge technologies to implement sustainable development is engaging digital twin technology in our practice. And the main goal, the main purpose of digital twins is to, to play different scenarios of controlling or managing of different objects, for instance, environment, in virtual realm, but not in reality. And it is believed that this could help us to improve our management and to achieve the goal of sustainability. And here is digital twin, which we try to develop. Sevastopol State University, in collaboration with the Institute of Natural and Technical Systems and other academic institutes, and you see that this concept contains three main levels. The first one is monitoring system, diverse monitoring system, which coupling with the satellite-derived data enable us to make a digital shadow of a region. In our case, it's coastal region. On different levels, like atmosphere, birds and others, soil, sea, humans. And once we have done it, we can model the whole variety of processes in this geosystem to achieve the main goal, to make an integrated and original decision support system. And on the right side of this slide, you can see a list of tasks for such a kind of regional decisional support system. And the main problem here is, the critical level here in this digital twin is monitoring system. Because monitoring system, especially in Russia, this system was created many decades ago, and there is a problem of merging new technologies in existing system of monitoring, and it is a purpose of creating a new technologies and implementing new technologies in this activity. On this slide, I try to describe an existing public demand in Russia. Indeed, there is a request for comprehensive and timely informing of government authorities, public associations, legal entities, individual entrepreneurs, with accurate and complete information about the state of the environment, as well as forecasting its changes. And the main feature, the main principle of this kind of system is to be as automated as possible. And there are a lot of federal programs, doctrines, and even society who holds this public demand. And in general, executive authorities like, for instance, Ministry of Nature and Environment or National Meteorological Service are capable to solve this task. But it's very hard to do. Why? This process, their process of storage, storing the data, pre-processing this data, and so on, is very long-lasting, and it's very time-consuming and resource-demanding. And the reason behind this is that these systems are document-centric. So primarily, you need to learn all documents which govern the process of monitoring. And after this, only you can use data. And to make this system more operable, you need to transit to a new type of system, data-centric system. And it's believed that ontology is one of the good technology which allow us to transit from document-centric system to data-centric system. It has a lot of features, very useful features, like, for instance, scalability, interoperability, and so on. And in our work, we try to create, to build such a kind of ontology-based model of monitoring system, which we believe to have some useful features like universality. We believe that our model has universal features. Of course, we in our construction, we initiate this ontology model by using well-known standards. You see, there is a society, W3C, which holds various standards on ontologies, and there's a standard like SOCA or SSN, which describes the observation system. But this ontology, the standard, has drawbacks. They do not hold entities about, for instance, meteorological stations or about a meteorological service or something about, for instance, documents which regulates this activity, monitoring as a process. So we take as a basis this standard ontology and modified it, and have modified it. Here on the slide is macrostructure of our ontology is presented, the concept. So we try to fill our ontology with different entities and classes which can be combined in these macro blocks, like objects of negative environment impact, territory, environmental monitoring, the results of monitoring, and so on. I forgot to tell you, to describe the main purpose of ontology. Not the purpose, what does it mean, ontology? Ontology operate with knowledge, not with commons, for instance, some programming coding. It's a knowledge which is projected into computers. So anybody, any professional can make his own ontology, and this ontology can be encapsulated in different informational systems, so decision support systems. Okay, let's move on. Here, our ontology is presented, and there are a lot of classes which can be combined again in different macro blocks. So you see that in the center of our ontology there is a modified saucer-based monitoring ontology, and other blocks. And especially our ontology has macro block like object-based ontology of negative environment impact. So our ontology, from one hand, holds entities about monitoring, and from other hand, has different entities about objects which impacts environment. This is about our modification of standard double 3C standard. We've added different classes about stations, about platforms, non-stationary platforms with sensors, about different documents, state regulations, manuals, and instructions. So we believe that our ontology is universal. Here you can see a list of selected questions, ontology questions, which our ontology can manage and can bring us a right answer. These questions and by means of semantic queries and computable classes can be encapsulated in decision support systems, and this is how this ontology can be used. The outlook for ontology-based digital model development. We want we are elaborating. We try to improve our ontology by including different objects from another standard ontology, NVO, environmental ontology. Next stage, we try to do in our elaborating a decision support system, which is based on our ontology in the field of air pollution control, and we plan to implement this DSS system in our Department of Ecology of our city. And this is almost the last slide. It is about an existing examples of analogous systems from the scientific literature. So it's very useful tool, sophisticated tool to make a transition from document-oriented systems to data-oriented systems. So this is now this is our results for now. Thank you very much.
My question is the following: your system, it is the cost for was made for coastal region. Is it difficult to adopt it for any kind of land, for example, mountains, agricultural fields, and so on?
Yes, of course, you're right. Our ontology, has no distinct features about coastal regions. It's just a title. Of course, every entity has some level, some rate of universality. They are universal. And we tried to do our ontology to be universal and to be capable to include all types of and manner of monitoring, not in coastal region, but on the land and in mountains and so on. For example, one of the part of this ontology is the ontology of satellite monitoring, satellite-derived data. So yes, our ontology can be used, can be applied not only for coastal regions, but for any type of environmental monitoring.